Now, let's just see what I'm saying here. I should warn you I can't read my own slides because my eyesight's not good. But this is basically what I'm going to talk about. So let me not pay too much attention to that. OK. Now, consciousness, which is what I'm trying to address, and my view about what's going on, as far as we can tell, although I don't know much about what's going on. Consciousness involves many different things, which one often concentrates more on what I'm going to concentrate on, such as, feelings of maybe perception of color or the feeling of pain or all sorts of things which involve consciousness. I'm just going to concentrate on one thing, which is the word understanding. The reason for that is because it's the only word that I can think of saying something serious about. I mean, I don't know how to say anything about perceptions of other kinds and so on. And understanding, well, I don't even really know what it means. And I've got three words. This is a laser pointer, which I probably won't be able. Oh, God, can anybody see that? I can't see it. We have three words here, none of which I would like to define. All I want to say is connections between them. One is, yes, I should get very close, then I can only actually see it. Intelligence. The word is intelligence, understanding, and awareness. And what I want to say is that our usual usage, although it's not the usage when one talks about AI, but the usual usage of intelligence is that it requires whatever understanding is, and whatever understanding is something which requires awareness. So I would say that to have intelligence or to have understanding, you really need awareness. Now that's, in usual usage, that's the case. But if you believe in artificial intelligence without any awareness, that would be a contradiction with these interpretations of the word. But anyway, I just wanted to give you my view. And what I shall be talking mainly about is understanding, because this is something where I believe, from a mathematical perspective, you can actually say something. So let's continue. First of all, let's say something. This is the chess problem. That's not really a problem. A chess position, which I made up, which if you give to Fritz, I was expecting that if you look at the position, you can see it's an obvious draw, because the black pieces, although there are many more of them than white, they can't do much. They're either trapped up in the corner up here, they can't get out, these pieces can't get out. You've got a free bishop can run around. One thing that's curious about the position, you've got three back bishops all on the same color. You have to check that that's a legal position. It is a legal position, but two of the bishops would have to have been bishoped by a pawn, and I think these two spots down here, and you can work out that it is a legal position. It's not a usual one, so it's not the kind of position that would have been encountered by any of these chess programs. And when you look at it, you can see there's nothing you can do. Nothing black can do. The bishop's on the wrong color to take any of the white pawns, and the white thing can't do much. So what happens? Well, you play against Fritz. Fritz is black, and Fritz loses the game. It was what I was expecting. Why does it lose the game? Well, because I have no idea how it's actually programmed, except I assume that it calculates a lot. If I go here, he goes there. If I go, he goes that sort of thing. Down to a certain depth. I have no idea how far. And then it tries to assess whether the position has improved or not. And how does it know that? Well, I guess it makes a count of the pieces, giving a queen value of 8 or something, or 9, and the pawns 1, and so on. So something like that. And it makes an estimate of whether the position is improved or not. Well, you see, it doesn't make any difference with this position. You just do, nothing happens. But what happens after 30 moves? Well, 30 moves, there is a 30-move rule which says the game is a draw if a pawn is not taken if a pawn is not moved and a piece not taken. And that's what happens. And so black, played by Fritz, I use an anthropomorphic terminology, thinks that the game should be a win for black, and therefore a draw is a disaster, and so therefore it sacrifices the bishop or releases the pawns or something like that. What it does is sacrifice the bishop. If you keep your king down here, That's the only thing it can do. It sacrifices the bishop, which is completely stupid. But then you see, well, you can march the king up, take the 2 black pawns here, move both pawns up there, get 2 queens. It's really quite hard to break through the barrier. 2 queens, and then you march your king right up in here, and you can checkmate after sacrifice one of the queens, and the other one gives you checkmate. So you can win against this really good chess player that can beat grandmasters and that sort of thing. Anyway, the idea here is that no matter how well it plays, it really doesn't understand the game of chess. And this is supposed to demonstrate that. Okay, well, that's one thing. Let me move on. I wanted about Go. You see, Go we know is you have AlphaGo or Alpha Plus, or whatever it's called, which seems to be able to defeat humans every time. I was thinking of maybe having a position like this, but I hadn't really got very far with it. So I thought of something else, which is that the game of Go is something where you start with a completely empty board, and then black puts a piece on, white does. All the pieces are identical. They're just stones. Black stone, white stone, black stone, white stone. And you have to make sure that you control more territory than your opponent. That's the idea. Controlling territory means you have a set of pieces that can't be taken. Let me not go into the rules of the game, but the point is that the AlphaGo or AlphaZero starts by simply knowing the rules, and that's all. And it plays itself zillions and zillions and zillions of times, and then having all this experience, it uses a bit of pattern recognition, I believe, and apart from that, it's just running through possibilities and seeing which wins. And the idea would be is that you present it with a position like one of these. I don't want you to memorize those because I'm hoping that maybe you have a set of positions, starting positions, which are not empty board, and you have things which you would never, ever have encountered in an actual game. And so the idea is that you play the computer against a human, and the human being would have the understanding of what you're trying to do, and the computer would only have its experience of playing itself zillions of times without any understanding. So the idea is that maybe a competition where you have random opening positions like this, that the human actually, to begin with, might well beat the computer. It would be interesting to see what happens. I think they're going to do it. I haven't actually, the thing has not been actually set up yet. I think I probably need a good Go player to decide on opening positions, and we'll see what happens. Anyway, it'll be interesting. This is something else I want to describe, which I wonder how good computers would be at doing. This is what's called, these are polyominoes. These are made out of squares stuck together in the plane, all equal squares, and you have different shapes. And the question is, can you tile the entire plane with these shapes or not? Well, the first 2 at the top are ones which you can. The next 2 are ones which you can if you have both of them, but each individually you can't. The one at the bottom a little more difficult to see why, but you can, you see. So this is an example of a problem. You're given a set of polyominoes, and will they tile the plane? That's the question. It's actually known to be a problem which in general you cannot solve by computation. And the reason I won't go into, but here's a nice example. I would love to see what happens if you gave it to a computer. Those 3 shapes at the top will tile the plane, but not in any repeating way. And this is an example which shows how you might start. And you can continue with this to cover the whole plane. But it would be interesting to see if you simply give the computer those pieces and ask it to see how far it gets. I would be very intrigued to see whether it could even get as big as this. I would give it a bigger pattern if it could get that one. Anyway, that would be interesting to do. I have something else which I thought of more recently. These are 3 shapes. These are not polyominoes now, but you have a regular hexagon, a square, and a regular dodecagon. And the idea is that you have to fill the entire plane with these shapes, matching the colors. So each edge you have to make sure they're matched. And the problem is, would it know? How far would a computer get just trying these? I'd be very intrigued to know. You have to have at least one dodecagon. If you can do it with squares and you can do it directly with squares. That's not, you have to have at least one dodecagon, and with that, how far can you get? And this is the sort of pattern that you make, and I'd be very intrigued to know whether a computer could get that, simply trying randomly one after the other. And here, if it does that one, see whether it could try this. I should say that these pictures are in fact made by a computer, but of course, according to the very specific rule in which you can, which you have to follow in order to assemble it. It doesn't repeat, again, it's non-repeating. I should make sure, should we go back to that, I think? Yes. If you want to know how this is done, there is an algorithm for deciding how to do this. The algorithm is to look through my collected works, and in one of my papers it tells you how to do it. I don't know any other algorithm that would do it. Well, not one that I would know how to tell somebody how to program. This one, well, let's continue. Okay, you see, the thing is about all those particular examples I showed you are really finite. Well, chess is a finite game. Actually, I should have had this in a different order, because those two tiling problems are really infinite, because you've got to tile the infinite plane. But I want to talk about infinite, because it really, whether you can have a computer do it or not depends on the infinite. If you really, the theorems about what you can do computationally, what you can't, always depend on the infinite. Sometimes people say, oh, well, the infinite, you can't think about the infinite. Of course, that's completely untrue. I can give you a completely easy statement that everybody would know. If you add two even numbers together, you get another even number. Well, that's a statement about the infinite, because it's about all numbers. So certainly you can say things about the infinite. Now, what's a good way of saying things about the infinite? Well, this is a Turing. See, how does a Turing machine think about the infinite? Well, thinking is a bad word to use here. But the Turing machine is this little thing in the middle, which you can see is relatively small. And the storage are these rather unruly collections of computer tape going right off. And you have to imagine they go off to infinity. And then you can wheel them backwards and forwards and so on. So that is rather a cartoon of a Turing machine with a finite set of rules in the middle, but an infinite potential storage. So that's the sort of thing that you have with a Turing machine. Now, here's a way you can talk about the infinite. This is the common way you learn at school, which is mathematical induction. You see, I'm talking now about the natural numbers. My natural numbers start with 0. These are the non-negative whole numbers. And if you want to know something which is, you want to prove something which is true for all natural numbers, what mathematical induction allows you to do, if you can prove it for 0, that's one thing, and you prove it, if it's true for n, then it's true for n plus 1, then you know it's true for all n. So that's something we learn at school. That's mathematical induction. And okay. Now, can you prove all things by mathematical induction about infinite numbers? No, you can't. And I want to give you, this is a version of the Gödel's theorem, which is basically Turing's version of Gödel's theorem. So let me say what it is. Suppose you have a set of rules R, which you could put on a computer, and they check whether a certain theorem about numbers is true or not. So you have a set of rules R, which are methods of proof. Now, you're supposed to believe that the rules R only give you truths. So you actually examine them carefully to make sure those rules, if the rules finally say, yes, it's true, then you believe it really is true, because the rules are correctly generated, and you can examine them carefully. Say, look, rule number 1, is that okay? Yeah, okay, I believe that. How about rule number 2? Not so. Oh, yeah, I see. And you go through them, make sure that you're convinced that following those rules is a proof. Suppose you believe that. That is to say, if applying your theorem, you applying your theorem to the rules, applying the rules to your theorem, or your suggested theorem, and if it comes out and says yes, then you believe it. Now, what does Gödel do? Gödel says that you construct a statement of just the kind that the rule would say whether it's true or false, or maybe go on forever. It might say true, or it might say false, or it might not come to any conclusion. If it says true, then you've got to believe it. That's the idea. Now, what does Gödel say? He produces a statement, G of R, that's at the bottom there, which has the property that it's true. You believe that it's true if you believe the rules only give you truths. So it's something which, if you understand what G of R is saying, and you can see what it means, the meaning of it is something which comes out as being true, provided you believe that the rules only give you truths. Yet, G of R, the same understanding of what G of R means, gives you that it cannot be obtained by the rules. Now, when I first heard about this way of stating Gödel's theorem, which I basically learned from a mathematician, logician called Stein when I was a graduate student in Cambridge, this is the sort of way he phrased it, which I previously had thought that Gödel's theorem told you the things you couldn't prove. But the point of this is that the statement this is just as good a proof, because you can see that it's true by virtue of your trust in the rules, even though you don't actually use the rules to establish its truth. You can't, because the rules, he shows that the rules cannot prove it, as long as those rules only give you truths. Now, people state this in different ways about consistency and all that sort of thing, but this was the way I first heard about it, and I found it absolutely stunning, because it tells you that our understanding of things cannot be encapsulated in rules, at least not in rules that you can look at and believe. And if you're looking at proofs of things that you are supposed to believe are true, then this tells you they are outside the method of proof. But what on earth's going on? Why is it that you can perceive the truth of that particular statement? Sometimes people misquote me and think that I say that you can prove anything by understanding. I don't say anything of the sort. That's not what's said. It's said there are certain statements that if you knew what the rules are, and if you trust the rules, then you can transcend those rules. And that's all I'm relying on here. But I think that's rather very remarkable. Now, I'm going to give you an example, which, you see, often people say, oh, well, the Gödel theorem is so complicated, nobody would be really interested in it mathematically. That's not really true. And a very nice example is this theorem of Goodstein, which I think was proved in 1945. And I want to describe it to you. I'll describe it to you in terms of a particular example, which I think is nice to do. What you take is a natural number, and let's choose this one, 1077. There's nothing special about that number. It's just any old number will do. And I want to, first of all, write it in a binary form. Well, we're familiar with that. That means you've got ones and zeros. And the ones and zeros, well, the ones stand for powers of 2, and therefore you're expressing your number as a sum of distinct powers of 2. That's exactly what the binary description is. Okay, so that's step number 1. You put your number as sums of powers of 2. But then you look at those powers, and you see, well, 2 to the 10th or something. 10 is not written that way. So let's write the powers also in terms of powers of 2. And then you may say, well, you haven't quite finished. I can't remember whether our next slide is doing that. Yes, and then you may have to write the numbers until the exponents, all of them, have come down to below 2. And you keep on going in the exponent, and it stops somewhere. So this is 1077 written that way. Okay, now there are 2 things I'm going to do this number. One of these things is to replace all the 2's by 3's, and there I've done that. That's procedure A. It makes the number much bigger, of course. Now it's a ternary number. And operation B, which is subtract 1. Okay. So it's gone up enormously and come down a tiny little bit. Now I replace all the 3's by 4's, and then I subtract 1. Now it's a little trickier here because you don't have a handy 1 sitting at the end, but it's like subtracting 1 from 1,000 to get 999. We're all familiar with that. And so that's the same procedure, but now in the ternary scale. Okay, then you replace all the 3's by 4's. What have I got to? And then you subtract 1. Or the 4's by 5, subtract 1, and the numbers get bigger and bigger and bigger and bigger. Well, you see how the sort of things, how much bigger they get. This is just roughly. You can see these powers of 10 getting much, much bigger, much, much bigger, much, much bigger, and finally they come to 0. That is the Goodstein theorem. The Goodstein theorem is that whatever number you start with, these pairs of procedures, it's a hare and tortoise, it's beat all hares and tortoises. The hare goes racing on and the tortoise eventually wins. Subtracting 1 always brings it down to 0. Now this was proved by Paris and Kirby to be a statement which you cannot use mathematical induction to prove. So it's, if you just learnt how to prove infinite things by mathematical induction, you'd never be able to prove this. So how do we know it's true? Well, I think Goodstein used this method. And what you have to know is that those numbers are pretty irrelevant. The pattern is what's important. And this, you have to imagine this. I've just blocked over the exponents, you see. And you have to imagine that those exponents are replaced by the transfinite ordinal number omega, and these are now ordinal numbers, and this is if you know this thing, these numbers have to come down to 0. So it's a theorem of transfinite number theory. Now you see, many people wouldn't know that. If you know transfinite induction, sure, you can prove it. Then you have another kind of Gödel theorem to that. But the point is, that I want to make here, is that even if you learnt somehow natural selection. We see here's the argument I want to make. There are all sorts of detailed arguments I made, but I think it's better to transcend all those arguments and think about how our understandings came about. Well, natural selection, I'm completely accepting that. That natural selection is how the notion of understanding came about. And you see in this picture in the distance, you've got our ancestors doing all sorts of useful things like building shelters, growing crops, domesticating animals and all that. And in the foreground, on the right-hand side, they're building a mammoth trap. And you can see there's a brilliant idea they had of how to build a mammoth trap. In the very foreground, we see a mathematician. Now, this mathematician is doing some quite sophisticated theorem of geometry, and he's about to be devoured by the saber-toothed tiger. The argument is that being a mathematician was not a selective advantage. I don't think it is anymore. It's still a selective advantage. I'm pretty sure it's not. But nevertheless, something, maybe our ancestors somehow built up the idea of induction. I have no idea whether they needed to think about infinite numbers. Hardly likely, but maybe they got induction. But they would in no way have seen Goodstein's theorem. There's no way that the understanding that one has of mathematics or of other things, which I claim is something which is not an algorithm. It's not, if it had been some very, very complicated algorithm in our heads, how on earth could that have evolved by natural selection, which has nothing whatsoever to do with building up complicated algorithms for solving things like the Goodstein thing. So I find that very hard to believe. In my view, understanding whatever it is, and I don't know what it is, but whatever it is something which is not an algorithm, not a complicated algorithm. I just see no way in which a complicated algorithm could give us the kind of understanding that enables us to do the sorts of mathematics that we can do. So there you are. That's the argument I'm making here. Okay, so that's the first part of the story. If our understanding is something not computational, what could it be and how could it have come about? Well, the claim I'm making here, and let me just see what I make because I can't necessarily remember what the slide said. Well, this is a question about really where do I think consciousness comes in the, say, animal kingdom. It's not even clear it has to be animals. I'm not totally convinced of that. It may be that, well, I'll come back to that in a minute. I don't think it's just mathematics. I don't want to give the impression that it's only in mathematics, good heavens. That's certainly not what I'm trying to say. Certainly that cartoon indicated that, because the understanding came from other things. But what about human consciousness? Well, yes, I think that's relevant. What about animal consciousness? Well, I don't think there's a clear dividing line between humans and animals. I certainly think apes, well, there's a conference going on here about apes, I think. I don't think there's that much difference. I don't think there's much difference, well, humans and elephants. I don't think, well, what about octopuses? They seem to be able to be a lot of indications that they're very intelligent and that I would believe that they're conscious. So where does one draw the line? Well, I don't know, but I don't think it's just at humans. I think it goes way down. And somehow it had a selective advantage, which, okay, was useful in mathematics and is also useful in other things. But the reason for concentrating on mathematics is that there you can say something, but it seems to be not a computational thing. But the question arises, if it's not that, and if you don't believe it's some mysterious woozy, what's it that comes into our heads? I don't believe that. I think it's something to do with physics. It's our brains are acting according to the same physics as is going on in that screen and that, so on and so forth. The physics is just the same. It's just organized in a way which is rather special, which brings things out, which can give us consciousness and understanding. Now, I thought about lots of things, about general relativity, about Newtonian mechanics. Yeah, let me just, before this slide, I really didn't want to bring that up quite so soon. So let's back up if I can. I was formulating these ideas when I was a graduate student, and I heard about Gödel's theorem then. And I was also learning about other things in mathematics, and then I went to courses that weren't specifically to do with what I was learning, which was pure mathematics. And I went to a course by Bondi on general relativity, and I learned about that, and I knew about Newtonian mechanics, and you can put that on a computer, or can you? There is a question because those laws of physics that we understand depend on a continuum. And what you put on a general purpose computer are things which are discrete. And so there is a question, is it that you can approximate the continuum well enough that you don't have to worry about this? I'm not sure what the answer is there. I don't think it is the answer, but it's a point that should be explored more, I think. Is the fact that the continuum is involved in our laws absolutely crucial, or isn't it? I don't think it is. I think the fact that one can approximate these things very closely, and the example, for example, of LIGO and seeing the signals from black holes spiraling into each other, and the very, very difficult calculations that are done to get these exact profiles that these things do, those are calculations which you use computers in the ordinary sense. You're using digital ideas, and you get this extraordinary precision which you can test in these gravitational wave detectors, and many other things as well. So I don't think it's Newtonian mechanics. I don't think it's general relativity. What about quantum mechanics? Well, now let's say something more about quantum mechanics. What is quantum mechanics? Well, the two pictures at the top basically are illustrating two aspects of things. So let's imagine here we have a laser which is emitting individual photons. And you see here we have in the middle a beam splitter or half-silvered mirror, which means that half the light goes through and reaches the detector on the right, half the light gets reflected and reaches at the top. And what you find is that every individual photon either goes to the right or to the top, and they behave like particles. But the other thing you can do is have an interferometer where I have now, if you look at the picture on the top right, we have two extra mirrors and another beam splitter, and you find that every time it's the detector on the right which receives the photon. So no, the particle description doesn't work. You have to consider that both routes are somehow felt out by the photon. So it somehow involves a superposition of two different things in the intermediate stage. So quantum mechanics depends on this idea of states being allowed to be superposed. So if A could happen, and if B could happen, then you have these other states in between where a bit of A and a bit of B, and it happens to be the case that the weighting factors of those two states are complex numbers. When I learned about that, I was utterly fascinated because I always thought complex numbers were very beautiful things, and now you see that the world seems to depend on these wonderful numbers at the smallest scale of quantum mechanics. But nevertheless, this doesn't give the measurement of you don't see superpositions, you see one or the other. And this is a process which is the second part of quantum mechanics, I've used the letter U for what's called unitary evolution, which preserves superpositions in these complex numbers. So it preserves them. The reduction of the state, that's what R stands for, is when you make a measurement and you do a completely different thing. You look at these numbers W and Z and you take the squared modulus of them. That's the distance squared from the origin in the complex plane. And those give you relative probabilities of two alternatives. A completely different thing. The unitary evolution chugs along without worrying about the fact you've got superpositions. And the reduction of the state gives you one or the other. And that's the way we do quantum mechanics. It's completely crazy, but that's the way we do quantum mechanics. Now, I was once invited to Denmark, to Odense, which was where Hans Christian Andersen had lived. And they asked me to give a lecture in honor of his 200th anniversary, which was to come in a year or two. And I think they had a series of talks. And I thought, what am I doing giving a talk about fairy tales? Then I did remember, of course, that I'd written a book called The Emperor's New Mind, which was based on, the title was based on The Emperor's New Clothes. And so I thought I would try to think of another. I didn't want to talk about that one. So I talked about The Little Mermaid as a way of illustrating quantum mechanics. I'll describe a little bit more of that in a minute. But partly I had the idea, in part of the story, there is the case when the Little Mermaid, when the sun comes up, the very first ray of light that hits her, and she dies. So I thought, well, the first photon coming from the sun, why don't we put a beam splitter in between so that this would put the mermaid into a superposition of life and death. So it was a Schrodinger's mermaid, you see. So I thought that was a good thing for the talk. That's not the way I'm using her now. I'm using her in a different way, which I'll come to in just a second. But it did seem to me there were various aspects of that story which illustrated what I wanted to say. And this was the measurement problem. And of course, people are probably familiar with Schrodinger's cat. He was demonstrating that you could, according to his own equation of how things evolve in quantum mechanics, you could put a cat into a state which was dead and alive at the same time. And he was trying to say, look, this is ridiculous. He was saying, my equation leads you to this. My equation, that's Schrodinger's equation, leads you to this. This is absurd. We're missing something. So Schrödinger was strongly of the view that there was something missing from quantum mechanics, and it was not simply his own equation. So this is the point of view I'm absolutely following him on. I'm following Einstein, who also said this. Dirac, surprisingly, said the same thing. So it's certainly you can appeal to authority if you like, except other people will talk about Bohr and Heisenberg and maybe have the whole battle one side against the other. I'm not going to do it that way. I want to describe, first of all, what the mermaid is doing. You see, what is that picture really? The top half of the picture is illustrating the classical world where you have sort of discrete separated things out there. And the quantum world is underneath the water, which is the world where things are all entangled and it's supposed to be all the seaweed all over the place, and it represents the entangled quantum world. And what is the mermaid doing? Well, she represents the reduction of the state. So as you see, she's partly under the water and partly over it, and she represents the process whereby, as you follow the tail right up to her head, whereby things in the quantum world become classical. So that's what the metaphor is meant to be here. Now, there are many ideas about what happens in how to explain how the measurement seems to take place. One of them is quite popular in Oxford, certainly in the philosophy department, which is what's called the many worlds interpretation, where you say that it doesn't reduce the state. The Schrodinger's cat is dead and alive at the same time, and when you go and look at the cat, you become in a superposition of seeing the cat and not seeing the cat, and you have to imagine that your conscious experience follows one route and not both. And I never quite understood why it should do that, but that seems to be the picture, that you have all these different things happening at once, and one's conscious experience seems somehow to thread through this and only perceive one world. And I don't really see why that should be the case at all. I know I've never experienced seeing superpositions of two things at once, but I can imagine experiencing that. And so my experiences don't seem to me necessarily to be of the kind where I don't experience superpositions. It's just that I don't, and I've never seen them. So the world that we experience seems to be one, a classical macroscopic world we experience seems to be one in which you don't have these superpositions. So my point of view is that there is something missing in quantum mechanics which makes those superpositions become one or the other. And there are lots of views about that. There are David Bohm had an idea one time. He didn't quite have a view which changed quantum mechanics, which changed how you look at it mainly. Girardi, Rimini, and Weber had a model which was really quite ingenious. And there are other models which are, in my view, fairly artificial. Most of them are physics models. You can have other kinds of models which involve in information or something like that. I don't see a rationale from any of for any of those models. They're ad hoc. They said you say, okay, something or other reduces the state. What I want to present to you is something which has a genuine physical reason behind it. And this is looking at not just quantum mechanics, where we have a really wonderfully confirmed theory, and people say how beautifully confirmed it is. That's true. And certainly you can have quantum effects over huge distances, millions of kilometers now, I believe. And you seem to see effects, quantum effects, which are preserved over that distance. Nevertheless, that doesn't tell you the whole story. And the thing I wanted to say is a conflict between general relativity and quantum mechanics. Well, now, you see, general relativity is now awfully well tested, extremely well tested. One can test the slowing of clocks by just raising them about that far. You can have clocks so precise that you can tell the general relativity effect just moving them a tiny distance, and you can see these effects. So general relativity is a very well-tested theory. Now, what's the basis of general relativity? It's the thing I'm illustrating here. This is, well, Galileo, maybe he didn't, maybe he did drop rocks from the top of Leaning Tower of Pisa. He certainly did experiments which showed that if you imagine him dropping a big rock and a little rock together from the Leaning Tower, that they would drop together. So if you were an insect sitting on one of the rocks looking at the other one, then as you fall, it would seem as though there was no gravity. And this is now illustrated very well by space travel. We have a rather modified 2001 space station that's not quite like the space station we do have up there. But the point is that the astronaut in free orbit is falling with the inertially and doesn't feel any effect of the Earth sitting right. You can see the Earth right there, but the astronaut doesn't feel the Earth's field, simply because, as with the Galileo rocks, he is simply following a free motion. Okay, now that is the principle of, principle of equivalence, which is to say that you can get rid of gravity by falling freely with it. Now, I want to show you that this principle is in conflict with the basic principle of quantum mechanics. That is the principle of superposition. So I'm not just plucking something out of the air. I'm taking the two basic principles of these two great theories and trying to show you that there's a conflict between them. Now, I don't want to go into the argument in detail because this isn't the place for it, but let me just describe the idea. Look at the top picture, you're imagining doing a quantum experiment on a table, say, and this quantum experiment, you want to take the Earth's gravitational field into consideration. So you want to say all the forces between things up there are dealt with. You want to include the Earth's gravitational field. Well, there are two ways you might consider doing this. The way that most physicists would do it would simply do what's called adding a term to the Hamiltonian, which describes the gravitational potential. So you do just the same as with every other force. You just put a term in there and you chug away, evolve the Schrödinger equation. You do what Schrödinger told you to do, and that's what you get. You get a wave function, that's the psi thing, which evolves with time according to the Schrödinger equation. Okay, no, Einstein comes along and tells you, no, you shouldn't be doing it that way. There is no gravitational field. It is simply the table's accelerating upwards or something, or whatever you think of it. So let's do it in a freely falling frame. And then that's the, I forget what colors I've been using. The freely falling frame is probably the purple one, is it? and you do it all over again. Now it's just the same as before, except there's no gravitational field in it. And then you transform back to what you had before, and you do a little bit of calculation, and you find that, well, what do you find? You find this equation that I think I've written down here. The big psi, I think, is the Einsteinian one, and the little one is the Newtonian one, where you put the term in the Hamiltonian. And what you see is they're almost the same in a sense. There's just a phase factor between the two. Now, if you know about quantum mechanics, you know that you can ignore the phase factor because it's what you want to do is work out probabilities, and when you take squared modulus, you don't see a phase factor. So you say, who cares? Well, actually, you should look a little bit carefully at that phase factor, because that phase factor has a t cubed up there. T is the time. And if you know about quantum field theory, you know that's spelling you a little bit of trouble, because it's telling you that the vacuum that you're using, or the form of quantum mechanics you're using, or quantum field theory, is actually different if you use one side from if you use the other side. It's called you're using two different quantum field theory vacua. And usually you don't care about that as long as you stick in one or you stick in the other. So you're sticking in the green one or the purple one, you're fine. Now, suppose we do something a little different. Instead of just doing an ordinary experiment with the Earth's gravitational field in the experiment I'm going to have a lump of stuff. This is this big lump I have at the bottom here. The brown one and the blue one are meant to be in quantum superposition. So on the tabletop is a part of it where I put those things in a superposition. And now we are in trouble. Because suppose I was a little insect here and I was trying to do quantum mechanics, and then I've got two gravitational fields here in superposition. So now I'm in trouble because I would be having a different quantum field theory vacuum for that one as for that one, and I'm not allowed to make superpositions. That's wrong. You can't do it. Quantum field theory says you just can't do that. You'll get infinite scalar products. You're in real trouble. So what this tells you is you're in real trouble. It doesn't tell you how to do it. So what do I say? Okay, I accept I'm in trouble, but I don't mind a little bit of cheating. A little bit of cheating will be that I just go ahead anyway. And I try to estimate the error involved in going ahead anyway. And I find out that this energy involved, I think it's down in the right-hand side, involves the difference in the gravitational fields. I integrate it. I have a local energy, and I integrate that all over space. And I find, I don't know whether my next slide is going to explain it or not, perhaps not. It does in a way. Let me say it first here. What you find is that there is an energy error or uncertainty of the system as a whole, which is, you can do a little calculation, and you find it is equal to you take the gravitational distribution of this one and subtract it from the gravitational distribution of that one. So I have a distribution of mass which is positive in some places and negative in other places. I work out what's called the gravitational self-energy of that difference. I call that Eg, and this thing Eg is an uncertainty in the energy of the system as a whole. Then I use the Heisenberg time energy uncertainty in the reverse direction from normal, but this gives me an estimate of the lifetime of that system. So I say it's like a decaying nucleus or something, which has an energy uncertainty which is reciprocally related to the lifetime of the system. So I say that this superposition will not last forever. It lasts for a certain length of time, which is basically the Planck's constant over this energy uncertainty. So that's the idea. And let's see what we've got here. I'm not quite sure I can remember. This is another way of expressing it. You see, here I have a space-time picture of what's going on. At the top picture, if you can see it here, you have the initial state. This is a lump which is in one place, and then I'm putting it in a superposition of two places. And the space-time gets distorted by the location of the lump. And as time evolves, the space-time is different from the brown one and the green one. They start to differ from each other. And the idea is how much is that difference between one and the other? And when that gets to a certain thing called the Planck volume, which is a basic quantum gravity thing, then it chooses one or the other. So this is the idea, and this is the picture. I'm illustrating it here, that there is a moment where the difference between them becomes of a Planck scale size, and Planck is the sort of quantum gravity scale. It's a ridiculously small measure of distance. It's 10 to the minus 33 centimeters. But when you put it all together, you find it isn't such a ridiculously small thing altogether. The time is, or so on. So let me not go into the details of that, but the argument is that there is a separation between the space-times, and a choice has to be made. This is what nature does. It chooses between one or the other. And according to normal quantum mechanics, we don't know which the one or which the other is. What I'm trying to claim is that whatever it is, it's something not computational. That's the loophole in the physics that we know, which we seem to have room for something which is non-computational. So the argument is that that's where it is. And we say now, Stuart Hameroff and I have the terminology that we call this an element of proto-consciousness, that somehow it's what consciousness, it's the building block out of which consciousness is built. And that's the element of proto-consciousness. I can't remember whether I've got anything more. Yes, well, the thing is, where is it in the brain? And I didn't know. I wrote the book, The Emperor's New Mind. I hadn't the remotest idea. And I tried to find out where it could be. And I knew about nerve propagation, and I didn't think that had a chance because there's too much disturbance of the environment. And I wrote my book, The Emperor's New Mind, hoping that it might inspire some young people to do physics or mathematics. I just got lots of letters from old retired people. And then I got a letter from Stuart Hameroff, who told me that I ought to know about microtubules, because that was his belief that where consciousness really resided in these structures, which are much smaller than the neurons, and they occur in all sorts of places, but the particular ones in neurons could be playing a role in consciousness. That was his idea, and it seemed to me this was very exciting because you have structures with a much better chance to preserve quantum states for a long enough time that you might have the reduction of the state playing an actual role. So this is the sort of picture that one has with these complicated connections between neurons and so on. And I think I better stop at this point, and Stuart will tell you much more what the modern view of what's really going on in microtubules and consciousness and so on. Thank you very much.